1 plus 1 plus 1 is 3. That is also 1 cubed plus 1 cubed plus 1 cubed, which is a slightly fancier way of saying the same thing. And it is the first case of a question that turns out to be genuinely hard. Which whole numbers can you write as 3 cubes added together? 29 works. 3 cubed is 27, and 1 cubed plus 1 cubed carries you the rest of the way. 36 is 27 plus 8 plus 1. 9 is 8 plus 1 plus 0, if you are willing to let one of the cubes be 0. And we are. So far, this looks like a puzzle you could finish over lunch. Take the number you want. Try small cubes. Stop when they add up. For a great many numbers, that is exactly what happens. There is one rule that changes everything, and we should be honest about it up front. The cubes can come from any whole numbers, positive or negative. -5 cubed is -125, and that counts. That single permission is what makes the problem hard, because it opens the search in every direction at once, and it means a hunt that has found nothing yet has told you nothing at all. Here is where this goes. One particular number under 100 sat on the unsolved list for 65 years, and when the answer finally arrived, it was 3 17-digit integers, found by about 500,000 volunteer computers. Before hunting, it pays to know which numbers are hopeless, because some genuinely are, and that part we can prove in about a line. Look at what a cube can be modulo 9. That just means the remainder you get after dividing by 9. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27, which is a multiple of 9, so the remainder is 0 again. 4 cubed is 64, remainder 1. 5 cubed is 125, remainder 8. Keep going and the pattern locks in place. Every cube whatsoever leaves a remainder of 0, 1, or 8. And 8 behaves as -1 here, since 8 is 1 short of 9. So the clean statement is that every cube is 0, 1, or -1 modulo 9. Add 3 of them and the total can only land somewhere between -3 and +3, which means the remainders you can reach are 0, 1, 2, 3, and their negatives. The remainders you can never reach are 4 and 5. So 4 is impossible, 5 is impossible, 13, 14, 22, 23, and on up the line in that pattern. Under 100, 22 numbers are ruled out this way, and no search will ever change that. That is proven, and it is very nearly the only thing here that is. Everything else in this video is a search. For the 78 numbers under 100 that survive the remainder test, the working belief is that every one of them can be done, and can be done in infinitely many ways. That is a conjecture of Roger Heath Brown from 1992. Nobody has proved it. Now go back to 3, the easy one we opened with. 1, 1, 1. There is a second way to do it. 4 cubed plus 4 cubed plus -5 cubed. 64 plus 64 is 128, take away 125, and you have 3. Both of those you can find by hand in a minute. In 1953, Louis Mordell wrote about this exact case. He said he knew nothing about the integer solutions for 3 beyond 111 and 44 minus 5, and that it must be very difficult indeed to find out anything about any other solutions. He turned out to be right in a way he had no instrument to measure. Nobody found a third way to write 3 as 3 cubes for another 66 years, and that is the shape of the whole problem. The small answers are trivial. The next answer after the small ones can be astronomically far away. There is no way to tell in advance which numbers are which, because 30 looks exactly as promising as 29, right up until you try it. So let's look at all of them at once, and let the pattern speak before I do. For every number from 1 to 100, take the smallest solution anyone has, and record how many digits the largest of the 3 integers carries. Sweeping every single triple with all 3 numbers under 5,000 is cheap, and it settles 69 of the 78. Those are the flat ones. 1 digit, 2 digits, now and then 3 or 4. Then 9 of them refuse. 30, 33, 39, 42, 52, 66, 74, 75, and 84. They do not refuse politely. 30 was settled in 1999, and its smallest known solution runs to 10 digits. 2,220,000,000 and change, cubed, set against two other cubes that very nearly cancel it. 52 held out until 2007 and needs 11 digits. 74 held out until 2016 and needs 15. Look at the shape of that chart. Nearly everything sits at 1 or 2 digits, and then a handful of numbers leap straight to 10, 15, 16, 17. The middle is empty. A number here is either easy, or it lives out past anything an ordinary machine can sweep, and there is almost nothing in between. The obvious way to hunt is to try everything. Pick a bound, run all three numbers from minus that bound to plus that bound, add them up, and see what you catch. With a bound of 1000 that is about 8 billion triples, and a laptop chews through it in minutes. Push the bound to 10 to the 17th, which is where 42 turned out to be hiding, and the number of triples is around 8 times 10 to the 51st. For a sense of that, the observable universe holds something like 10 to the 80th atoms. Brute force is finished before it begins. So you go to the algebra, fix the third cube, whatever it happens to be, and call everything left over m. Now you need two cubes that add to m, and a sum of two cubes always factors. X cubed plus y cubed equals x plus y, times the quantity x squared minus xy plus y squared. Notice what that buys you. The quantity x plus y has to be a divisor of m, which is already a huge restriction. And it cannot be large either, because that second factor is always at least 3/4 of x plus y squared. So the sum of the two unknowns is trapped inside a range, and it has to divide a known number. That is the crack in the problem. You stop sweeping a cube of possibilities and start walking a list of divisors. Andrew Booker took that idea and sharpened it. Rather than run through every possible third cube and factor each left over, he ran through the divisors, and for each divisor he solved a congruence that pinned the third cube down to a few remainders. Almost everything gets skipped. The work stops growing like the cube of the bound and starts growing roughly like the bound itself, which is the difference between impossible and a few weeks. In March of 2019, he pointed it at 33, which by then was the smallest number under 100 that nobody could write as 3 cubes. It ran about 3 weeks on a university cluster, and it came back with 3 16-digit integers. 8 quadrillion, 866 trillion and change, cubed. A negative partner of almost the same size, and a third number roughly a third as long. Cube those 3, and you get numbers carrying 48 and 49 digits each. Add them, and every digit cancels except a 3 and a 3. That is what these solutions look like from the inside. 2 enormous cubes that almost annihilate one another, and a third that closes the remaining gap exactly. 65 years of tables, and 33 was gone in 3 weeks once the search was aimed correctly, which left exactly one number under 100 still standing, 42. It had been sitting on the list since 1954, when Miller and Woollett ran the first proper machine search and published, among other things, what they had failed to do. Booker teamed up with Andrew Sutherland at MIT, and instead of one cluster, they used Charity Engine, which borrows idle time from volunteer machines all over the world, roughly 500,000 of them. Over 1 million hours of processing, which is more than a century of work if you ran it on a single core. In September of 2019, it landed. 3 integers, each 17 digits long, 1 negative, 2 positive. Cube them and the first 2 carry 51 digits apiece. The third carries 49. Watch how the cancellation works. The two 17-digit giants differ from each other by about 100 trillion, which is a 15-digit gap inside 17-digit numbers, so they agree in their leading digits and then part company. Their cubes add to a 49-digit negative number. The third cube, 49 digits the other way, wipes it out and leaves 42. Not approximately 42, exactly 42, in whole numbers, checkable by hand if you had a very long afternoon. That was the last one under 100, 65 years after it went on the list. Now the question that actually bothers me. Why would 42 hide at 17 digits, when its neighbors were done with 2? There is a heuristic that answers this, and it is the reason nobody expects the remaining cases to get easier. Count the pairs of whole numbers whose size is under some bound. There are roughly the bounds squared of them. For each pair, the leftover has to land exactly on a cube, and among numbers of that size, cubes are spaced about the square of the bound apart. So the chance that any particular pair works is about 1 over the bound squared. Multiply those, and the expected number of solutions does not grow with the bound at all. It grows with the logarithm of the bound. Every additional solution costs you an exponentially larger search than the one before it. Put that in digits. Going from 10-digit numbers to 20-digit numbers does not double your haul. It adds a fixed handful of solutions, and to collect that handful, you had to do 10 billion times as much work, which is exactly why the chart has no middle. Solutions are spread evenly across the number of digits, rather than across the numbers themselves. A number that missed at 4 digits has no particular reason to appear before 17. There is a coda to Mordell's Remark, and it is my favorite part of this. The same charity engine run that settled 42 was also pointed at 3, the number Mordell had said would be very difficult indeed. For 66 years, the complete list of ways to write 3 as 3 cubes was 111 and 44 minus 5. In 2019, a third one appeared, 21 digits each, 569 quintillion and change, a negative partner that agrees with it for the first 9 digits before drifting apart, and a third integer about 1,000 times smaller than the other two. Those first two agreeing to 9 digits out of 21 is precisely why the whole thing can collapse to 3. Mordell wrote his sentence in 1953 with a table and a pencil, and he was exactly right about the difficulty. Settling it took a planet's worth of spare processor time. If you remember one thing from this video, make it this: a solution being enormous is no evidence at all that it fails to exist. For equations like this one, enormous is the ordinary size, and the small solutions are the accident. So where does this stand today? Every number under 100 that survives the remainder test now has a solution written down somewhere. Above 100, the open list is still there. 906 fell in 2021, again to Booker and Sutherland, again with 17-digit integers. The smallest number whose status nobody has settled is 114. Nobody has produced 3 cubes that make it, and nobody has shown that none exist, because the only proof technique anyone has for impossibility is the remainder argument, and 114 passes that test cleanly. 114 leaves a remainder of 6 modulo 9, which is allowed. Heath Brown's conjecture says 114 has infinitely many solutions, and we simply have not looked far enough. Everybody believes it, nobody can prove it, and that is the odd position this problem occupies. We can prove exactly one thing, which is which numbers are impossible, and it takes about a line of arithmetic. Everything else is an open-ended search running against a conjecture that promises the answers are all out there somewhere. For 114, somewhere might mean 20 digits. It might mean 50. Until a machine finds it, the honest answer is that we do not know.